join the mailing list, make sure you send the word webinar to our email or to our WhatsApp number, which you can find on the chat. This is strictly about the seminar. There will be no spam. Also, you can check our future talks and previous talks on our future talks on our website, and all the previous recorded talks on our YouTube channel, which you can also find on the chat. So today we're very pleased to welcome Mariel Sáez from Catholic University of Chile, which incidentally shares the top of the rankings in Latin America with us. So cheers. Telling us about, it generated a lot of debate in here. I have no idea. People got really worried. So well done. Today we're going to hear about short-time existence for the network flow. So thank you, Mariel.
Well, thank you very much for the invitation. And I have to say, this is the first time I'm presenting with Meet, so some of the tools I'm not aware of. So please interrupt me if you have any questions, because I cannot see anyone. I'm only seeing the presentation at the moment. So just speak out. I will try to answer the questions if I can. The work that I'm going to talk about today is joined with Jorge Lira, Rafe Mazzeo, and Alessandra Pluda. And it's been a long ongoing work because we've been trying to include many different details that hopefully will be out in the coming months, the paper. And I'm going to start by trying to explain a little bit the context. What do I mean by the network flow? And I'm going to start by defining what is mean curvature flow and curve-shortening flow. The mean curvature flow is the gradient flow associated to the area functional, which translate into PDE, a geometric PDE. That is the one that is written down there, that says that the speed in the normal direction has to be proportional to the mean curvature. The sign there is related to the direction that you pick, the normal, of course. But the idea here is that if you're convex, then you should be shrinking, you should be contracting. So that should give you an idea what the sign is. The normal is the outward normal here. When n is equal to 1, this is called usually the curve shortening flow. So I may say, because soon for me n will be always 1, curve shortening flow. And I just mean the same thing, but for curves. And here, if I were on the tablet, I would draw the picture of what's happening here. But the first example that one can compute very explicitly is the circle, or the sphere is exactly the same computation, and show that in finite time that you can compute super explicitly, because there you know how to compute the mean curvature. During the evolution will be always a circle, but in finite time that depends on the initial radius, this will converge to a point. So this is going to be shrinking and faster as this thing gets smaller, and eventually it's going to be a point in finite time. So in that sense, I mean, this thing stops being a curve or a surface in finite time. So from the analytical point of view, you can see that it develops singularities in finite time. In the non-one-dimensional case, singularities can be quite complicated. Again, here I was planning to make a picture of what's happening, but I'll try to explain. And soon, as I said, everything will be one-dimensional to me. This is a little bit to justify that everything that although I will be doing is one-dimensional, if I wanted to introduce more dimensions, it's much more complicated. So in this example, what you have to think is that you have a long neck and two balls. This is usually called the dumbbell example. And depending on the proportion of these things, a cylinder, when you compute the evolution, is something that is converging to a line. And a ball, as I said before, is something that is converging to a point. But if the radius are balanced in the correct way, what you will see is that the cylinder is going to, in some sense, shrink faster than the spheres, and you're going to have a pinching in finite time. So singularities are not just as the first I described. You're not only contracting to a point, so you can have things that are more complicated, like a neck pinch. And in general, the problem of classifying singularities for mean curvature flow is something that in full generality is open, it's not well understood. Only under very restricted, somewhat restrictive conditions, you can say more about how is the development of singularities. Which implies that in general, the study of mean curvature flow is a lot about trying to understand how singularities are. So there's a lot of theory on how to study singularities.
Mariel?
Yeah.
Let me just quickly stop you there.
Yes.
Are people having difficulties with the audio? Because I'm hearing just fine, but somebody's complaining about the audio. Is everything
fine too?
Yeah. So maybe it's a local problem, not a global problem. Okay, please go on, Mariel. I think it's fine.
Okay. So as I was saying, the one-dimensional case is very special somehow in this embedded world when everything is smooth. And in fact, you can show that if you have something that is embedded, a curve that is embedded, this is going to converge in finite time to a point. It's going to become convex in finite time, and it's going to converge to a point. So this is sort of like the best case scenario, the case that is better understood among all the things that you can study in mean curvature flow, or curve shortening flow in this case. Yet, I'm just writing this theorem here to compare it with the case that I'm going to be interested in a few minutes. Okay, so as I said before, in general, the idea is to see how you deal with singularities. And for that purpose, there have been definitions of how to flow objects that are not regular manifolds. It could be something like what I drew on my left, I guess. I don't know. I never know, like from the, I guess on the left, that has some sort of corner there, or something that is directly not a manifold. That is like the thing that is drawn in red on the right-hand side, that is, it's a varifold, but it's not a manifold. And for these things, there have been weak definitions of what mean curvature flow or curve shortening flow should mean. In fact, one of the probably earlier works on this direction is the work by Brachy, and what now is known as the Brachy flow, and he gives a definition for what should be mean curvature flow of varifolds. But the objects that you obtain as a result, of course, are varifolds with all the issues of regularity that you have with that. And on top of that, the Brachy flow has a problem that is that the evolution is not unique. I mean, you have high non-uniqueness in the case of Brachy flows. For a given initial condition, you can have many solutions. And I will go back.
Can I ask a question? Is this flow closed for varifolds? So is the limit a varifold? So manifolds it's not, right? The limit can be singular.
Yes, exactly. This is a good question. I think you need a little bit more regularity on the varifold. I think you need integer varifolds, and then you can say something. But okay. Yeah.
So there are still compactification issues even if you begin with varifolds.
Yeah.
Okay. Cool.
Not even completely general value. What I'm going to talk today is something that's in between sort of Brachy flow and regular flows, and that's why I'm mentioning this point here, because everything that I'm going to talk about today can be seen from the point of view of Brachy, but has this regularity issue that I sort of want to, I don't know, improve in some sense. I don't know if regularity is an improvement, but that I want to see in a more regular fashion, I guess.
Thanks.
Okay, so this is what I said before. And here, unfortunately, I was planning to draw the network. I don't know if there's a tool here that allows me to draw things. Let me give it a try. No, it doesn't allow me to draw here. No, I don't have a tool that would allow me to write. So, okay, a network is going to be a family of curves that meet at their endpoints, and at the boundary you have to put some sort of condition. And I'm gonna show here a piece of a network that is what I mean there. So here, for instance, I have three curves, like the picture that I had 2 slides before, and each of them, I'm gonna ask them to evolve a curve shortening flow. And on top of that, I'm gonna assume here, this in the previous picture was supposed to be connected to other curves. And I'm gonna assume at the outer boundary is the one that touch the boundary of the set that was this oval that I drew here. You have to impose some sort of condition that can be Dirichlet, Neumann, different things. Today, I'm not going to talk much about that, but I'm going to always assume that I have a Dirichlet boundary condition just to set something. Many things that I'm going to say also work for a Neumann boundary condition. So just to say that you need to impose something, although I'm going to ignore it most of the time. Okay, so I'm going to have now a system of curves, each of them moving by curve-shortening flow, meeting at points that I'm going to call nodes. When I talk about nodes, are these meeting points. These, of course, are variables, but I'm not looking at the evolution in the sense of variables because I'm asking for each of the curves to be regular, to be evolving regularly. And somehow you have a singularity within the flow that is this node. It's not a singularity per se, but somehow in terms of the way you pose the problem, it can be seen somehow as a singularity that is preserved through the flow. And that's what I meant, that is something in between a regular evolution and a Bragg evolution, a variable evolution. Okay, let me say a few things about what do you need to ask about the flow at that node, at that central point, because of course I want this to be a network for all times. So somehow I need to impose a boundary condition there that tells me that this is going to be a network for all times. So that would be a meeting condition. But from the analytical point of view, you need another condition to have the equation as a PDE well posed. And what I want to discuss a little bit is what should be that other condition. So the first is the meeting condition, and the second condition is this condition that curves should meet in groups of 3 at 120 degrees. And I want to try to convince you that this is a reasonable condition to impose at that node. And for that, this is the part that I would like to see people, to see if I lost everyone or not. But the question is, in these two pictures, if you were looking for a minimizer, what would be the minimizer? How does a minimizer, in this case, look like? And this is maybe a bit more than a calculus problem, but it's an elementary problem. It's something that you can do with geometry, elementary geometry tools. And I don't know if anyone at this moment wants to say something about what should be the solution in this case.
I know the answer, so shut up.
Okay. Anyway, so if you know the answer, probably you think I'm extending this too much. If you don't know the answer and you're trying to compute what this thing should be, I'm gonna tell you that in both cases the solutions are these. When you have three lines, that have equal angles, 120 degrees, in case such configuration exists. Because of course, if you take points that are too close together, you don't have a configuration like this. I mean, if you allow the points to be anywhere in the circle and the 3 points are very close together, it's gonna look more like a wedge. I mean, like this, I guess, if the points are up there. But in general, like this. In general, if you have a configuration where the 3 lines can meet at 120 degrees, this is going to be the minimizer. And when you have 4, the first instinct is to think that it's going to be 2 lines, but it's not. Actually, this is a better configuration, not precisely drawn there, but somewhat. And you have 2 nodes that have just 3 curves, and each of these angles is again 120 degrees. So the condition that I imposed before, or that I said that I'm going to impose, is related to that minimizers locally should satisfy this condition, that you're meeting in groups of 3 at 120 degrees. And moreover, this makes the problem well posed in analytical terms, in terms of the PDE. So this is going to be my flow now. This condition is known as the Herring condition, historical reasons. This problem first arose actually in material science, and Herring imposed the condition. That's why it's called the Herring condition. But yeah, as a PDE, this is going to look basically like this. You have a family of curves. Each of them, the speed in the normal direction is going to be the curvature. And here I chose the other normal, so I changed the sign from my first slide. Sorry about that, I just realized. Then you have the condition that they should meet in group of threes, and this is the condition that is written here. I could at least highlight that. This is that you're meeting at the central point. And the condition below is that the sum of the tangents are 0. And if you think a little bit about it, that means that the only possibility that this happens if you have 3 curves is that they're meeting at equal angles at 120 degrees. So this is a way of just writing that you have that all the curves meet at equal angles, and those angles are 2 pi over third or 120 degrees. So this is the problem that we're looking at. And for this problem, as I said, as a PDE, this is well posed, and many people have studied short time existence. So if you study with something that is already a regular network, and sometimes even you need further conditions. In the first papers, they impose that the meeting condition is satisfied to higher orders. I'm not going to go into detail about that, but it is known that if you start with something regular, then you have short time existence. There are very few results for long time existence. There is some work by Mantegazza and other collaborators, Novaga, Tortorelli, Magni, Alessandra Pluda, where they look at long time existence results. And this is much more challenging, in fact. I mean, this is not so well known in general. Anyway, so let me talk a little bit about the singularities in this case. As I said before, in the area, more or less, this is the big problem, sort of understand what the singular behavior should be. And here I have 4 examples that I wanted to actually draw a bit more, but I won't be able to, so I'll just say it, I guess, slowly. So I tend to go too fast when I cannot write. That's why I always try to write a few things when I'm giving a talk. You have here 4 examples, and you might be wondering why these are different examples. These are just loops, and the last one is not a loop. So I'm going to first talk about the case of loops, and I'm going to remind you something that I said just before. That is, when you had a closed curve that was embedded, that curve would converge in finite time to a point. That's why I wrote that theorem here. That's a general fact about closed embedded curves. And here loops, you may think that this should work the same. So let me say a word about how you prove that result. The thing is when you have an evolution by curve shortening flow, because this is 2-dimensional, it's very easy to compute the area, the evolution of the area that is enclosed by the networks. And if you do that exercise in this case, you're going to see the angles. Something that doesn't exist, of course, in the embedded case. And when you introduce the angles, you're going to see that depending on how many angles you have there, so how many nodes you have there, the evolution of area is going to look different. So in the first case, when you have less than 6 sides, the evolution of the area is going to behave like in the regular case. It's something that is going to contract and converge to a point in finite time if nothing else happens. This is assuming that there are no other types of singularities. That is something that I'm going to talk about in a second. When you have 6 sides, you are going to see that the evolution of the area is constant. So the area is going to be preserved for all times unless something else happens. And when you have more than 6 curves, the curve is going to expand. In fact, it's not going to contract. This is going to, the loop is going to grow, and the area is going to grow, and you can be very precise on how the area is growing unless something else happens. And the something else that may be happening and that you have to consider as a possibility is the last picture that is in yellow below there, is that you may have sometimes arcs that are collapsing in the evolution, and you're losing regularity because if the small arc that is in between collapses, then you're going to have something that has 4 curves coming out of one node, where these one nodes come from the collapsing of the two other nodes. And this may happen even in the loops. I mean, it may happen, it's not known at least that it doesn't happen, that you have one of the curves sort of disappearing within the evolution and changing sort of the regime that under which it's evolving. All these are things that may happen, or at least that it's not known how to discard that they happen in general. In very particular cases it's known, but in general it's not known. And well, here is what I was gonna write, so I'm gonna skip that. I'm just gonna say that you could have collapsing of not one curve, but also of many curves at the same time. So you can have not only 4, you can have more curves coming out of one node after a finite time in principle. So the interest of the result that I'm gonna talk about today, it's exactly trying to see what should be the existence, or if we can give an existence result when you have one node and more than 3 curves coming out of that node. Can we say that we have some sort of short-time existence, and how does it look near that node? Because of course, by short-time existence, I mean that I'm starting with something that is not regular, but I would like, at least in a short time, to be regular. So immediately I want it to become regular and to remain regular for a short time. So I don't know.
To be clear,
yeah.
To be clear, the order boundary of the curves, this is on a fixed manifold, on a fixed submanifold?
This is a good question, and you can consider different things. You can consider them, in a sort of bounded manifold with a boundary, and that this has some sort of boundary condition. Dirichlet Neumann or something that is reasonable for the problem, or you can think that they're unbounded, and then you need to prescribe some sort of decay. And from what we do, you can prescribe them to be decaying to lines. I don't think you can prescribe things that are more wild than that in principle.
Because if it's curve shortening and you let them free, why isn't it just going to shrink? Period.
Yes. No, you cannot let them free. You have to pin them down somehow to something. But you can think about them not being bounded as well. This is also, and I'm going to talk about a case where they're not bounded, and you can say things. In fact, that's an important example in this case.
Okay.
I don't know if there are any other questions before I go to the main result. This is sort of like my introductory part, and I'm just thinking there's one picture that I will need to draw somehow, and we'll see how I can manage that. Well,
go ahead.
If not, let me tell you what the theorem is. We're going to assume that we have a network that all the curves are C2. And we have one interior vertex that is not regular. Then at all times, we're going to have, there will be a positive time that for all times in between that positive time and 0, the network is going to be regular, and it's going to be converging to this initial condition in a sense that I'm going to try to explain in the proof, because it's related to the way that you prove, but it's a quite strong sense. And the flowouts, by this I mean the behavior of the node immediately after 0 is going to be classified by special kind of solutions. There are the expanding soliton solutions of the flow that I'm going to try to explain a little bit. And this is a picture that I'm going to be missing, but I'm going to try to see if I can draw it somehow. Okay, so there are several things here that I will have to explain before doing the proof. In particular, what are the expanding soliton, and in what sense I'm talking about convergence. Something that it's a relevant question here, and that I've been asked before, so I'm going to answer it before in case someone has the question. Whether the C2 regularity is the correct regularity. Pro is not the optimal one, in the sense that when you have these things that are collapsing to a point, you cannot guarantee that at the node you will have a C2 bound in general. So the proof is going to be oriented eventually to have less regularity, to have something like integral of curvature squared, L2 norm of K being bounded. I don't know if I'll have time to talk about that, but for now, you can assume that it's actually C infinity, just to give an idea, a sense of what the result looks like and what the proof will look like. This result has been cited before by Tomil Mannen, Andre Neves, and Felix Schulze. And the thing is, in their approach, this is very one-dimensional, and we want something that somehow can be translated to the more general and more difficult problem. And the methods are different, so we want to give a description, basically, of the singular behavior that is much more precise than the the description that they give. I mean, some of the things that they use, they're very particular to this problem, and we sort of want to give a proof that doesn't require that particularity that cannot be translated to, for instance, the same problem in higher dimensions. I'm sure that our proof will have other issues that probably are better from their approach, but it's a different approach. And the methods that we used come from microlocal analysis, and the microlocal analysis is basically a tool that allows you to describe singularities in a better and more precise way. And I'm gonna be trying to explain what I mean by this, but I guess just in order to do this on time, I'm just gonna give an idea, and I'm not gonna go over all details. But if someone wants more details, I can also talk about more details. And here there's something I wrote that in general we expect this to generalize for more problems that are of conic type, and this basically means that after you look at the equation in a suitable way, you can think about the triple point, or the junction that is not a triple point in this case, but the junction there, to be a conical type of singularity for the evolution. The equation tells you that this should be treated as a conical type of problem. And I'm gonna be more precise about this when I talk a little bit about the proof. So the first thing that I want to do is sort of give an idea of what is microlocal analysis, and if there's any microlocal analyst here is gonna be probably mad at me for the simplification, but I'm just gonna give a huge simplification of what this means. And it's basically sort of trying to introduce better coordinates and to do the estimates in coordinates that tell you more about the singular point. So for instance, when you have something that is explained in polar coordinates, of course the polar coordinates in some sense are not, I mean, the theta parameter of the polar coordinates is not important when you're talking about r equal to 0. But if you were to treat a problem from the point of view of microlocal analysis, basically you would try to incorporate the information that the theta angles gives you at the 0 point. And this can be understood that basically the origin, you're blowing it up and thinking about it as a piece of the sphere. In this case, because it's a corner, is theta between 0 and pi over 2, if we're just thinking about the two-dimensional thing. And so basically, in some sense, what I'm going to be doing is describing the problem in suitable coordinates that are like polar coordinates. But I have to respect the fact that here, if you want what would be the x-axis, is going to be my parameter that parameterizes the curve, and the y-axis would be the time. And in that sense, if you want to respect the equation, and this is what is in the next slide, you have to consider that for a parabolic equation, here I just wrote the heat equation because, I mean, it's more clear maybe what I'm gonna say. The homogeneity of the time derivative and the spatial derivative are different. So basically that can be addressed by considering that the homogeneity of these two things are different. So r squared, instead of being y squared plus x squared, is gonna be t without the square and x squared. This is the sort of polar coordinates that you're considering here when you write the equation, and we're gonna be interested of what is happening at basically r equal to 0 and the angular coordinate that I'm gonna try to express in this way. Just as a matter of fact of writing the equation looking nicer, this is a better set of coordinates to choose, x over root 2t. The 2 is just for some 2's not to appear in the equation. I mean, you can take root t as well. The 2 is just a cosmetic choice for things to look better when you're computing things, not to be forgetting 2's all over the place. And this, if you think about it in polar coordinates, this would be something like cotangent theta, basically. This is like the s if you're thinking about polar coordinates. And these are very good coordinates if you're far from the initial time, from t equal to 0. So basically, the computations that we're gonna do, or that if you want to get more familiar with this type of coordinates, you can do the same exercise that I'm gonna describe in the case of the heat equation using these coordinates. We're gonna write the equation for these coordinates, and then to match it with the initial condition, we're gonna consider a different set of coordinates that is basically better suited for the initial condition, and these are the other set of coordinates that is written there. And then if you want to, I mean, this is when I say blown up coordinates, I'm gonna be referring to these kind of coordinates, so to these things here, and I'm gonna concentrate in a minute when I go back to my problem on trying to understand what happens with this new boundary that I'm creating. Yeah. So let me just say one more thing. Just thinking about like this picture here on the right-hand side. Under this perspective, you have to think that the problem has the usual boundaries that it had before, that is t equal to 0, x equal to 0, that corresponds to the point where the node is, but you have an extra boundary that you introduce by introducing the polar coordinates that corresponds to r equal to 0, and is some description in theta, or s in my other coordinate, s between 0 and infinity, that we will have to give. I mean, we'll have to give an extra sort of boundary condition of this new boundary that I am adding by introducing new coordinates. Okay, so given that idea, here I say a few words about how you would solve the heat equation, but I'm gonna go back to that in relation to my problems. I'm just gonna skip it for now, although I think I have time. But maybe just to set the discussion into what I'm interested in today, is the other word that appeared in my theorem, that was the expanding solitons of the flow. And for this, I'm going to again start by telling you a little bit about the expanding solitons for regular solutions, meaning when you start with something that is just a real cone, a regular cone, or two curves, because we're in one dimension. But this works the same way if you have two planes. I mean, think about two lines for now, and I think it's enough at the moment. And I think I drew a picture. So the idea is that you have two lines, and you want to know if there is a solution that is a multiple of a fixed curve that at the initial time is going to look like this. And here I try to draw the picture of that. Basically, you have the fixed curve that is this gamma 0. And for all times, I don't know if I can highlight it. I can highlight here. Basically, no, I couldn't highlight the gamma 0, sorry. But the gamma 0 is a fixed curve. So the solution for all times is basically a multiple of this gamma 0, and I parameterize in this way, on one hand, to be consistent with the coordinates that I introduced before, but also for you to see what are you seeing at time 0. So it's not very difficult to see that basically at time 0 what you're seeing is the tangent at infinity of this gamma 0 and the tangent at minus infinity of this gamma 0, and the corner comes there because the two tangents are not the same tangent. Yeah, so these are known to exist. I don't know who was the first person to introduce them, but for me, the reference that I would suggest is the work by Eker-Husken on entire graphs. I don't know if there's anyone before introducing these kind of solutions. And these are going to be relevant for my discussion because the curves, the self-similar solutions in the case of networks are going to be pieces of these solutions that were described by Eker and Husken. So the equivalent problem in the case of networks is to consider the following kind of, here I'm saying a little bit more about the self-similar solutions. Sorry, I forgot. I mean, you can give a precise description on how these gamma zeros are going to be. And you can do a long discussion about just how these self-similar solutions look like. But let me, yeah.
Can I just try and get my geometric intuition straight? Yeah. So if you can go back one.
Yes.
There. So just to be clear, so the expanding soliton in this case would be in some sense the same curve, but the sort of as you get closer and closer to the angle, then the curved region gets smaller and smaller, right? But with the same behavior. That's it, right?
Yes, that's it. And the curve is regular for every positive time, and it sort of degenerates at infinity because, I mean, you're just expanding it in a way that at the end you're only seeing the tangents at infinity.
As if the region in which it's doing the little curve is getting smaller, right? So it's
right.
Okay, so I understand. Okay, cool. Thanks.
Okay, so you can give a very long discussion about how these self-similar curves behave. I mean, this satisfies some equation as well. The curvature is equal to the curve times the normal. This, in fact, can be seen, and I'm not going to talk too much about this, but I'm going to mention it later, so I'm just going to say it. These curves are, in fact, geodesics in a suitable metric. You can impose a metric on the plane that has these curves exactly as geodesics of that. And for the network, basically what you're looking for is something that at the initial time is just lines. But for positive times, it's going to be a geodesic network. So basically a network that is composed by curves that are like the ones that I described before, or pieces of that curve, rather, and they're going to be asymptotic to these lines. And here I had a blank page where I was going to try to draw what is coming out of that. But what is important to discuss, and let me see if I can find some way of writing here, I think. There should be a way of writing, I guess. I don't know if anyone knows if there is a tool here to write. Oh, no, I mean only highlighting, fortunately. But basically,
I suppose you can try drawing with our imagination if you just describe what you would like us to see.
Yeah,
we can try that.
Describe it with 4 curves because it's easier than with all this, but you can do the exercise with more. And this is sort of related to the picture that I drew before when you were minimizing. Basically, it's going to look like 2 things like this. But when you evolve, you're going to have these things separating in 2 triplets. This is by the picture before, I mean this one, when we were talking about minimizers. I'm talking about this one. It's going to look like this. These, of course, are not going to be straight lines. They're going to be curves that are geodesics in this other metric. And this curve, this intermediate curve, this curve here, no, I cannot even highlight that, but the curve that is joining the 2 nodes is going to disappear at time 0 under the same effect that before all the rest of the curve was disappearing. Basically, the 4 lines are going to evolve in something like this. Of course, here, just by saying that, if you have something regular, you can imagine, and this would be a nice picture if I could draw it, but I hope you can imagine it, that you can separate like this, or you can separate like that. And when you have, I mean, you can separate with the curve like I'm drawing it here, but you can also be separating on the other direction, namely like that vertical line that I have joining the 2 nodes could be a horizontal line. And when you have something that is fully symmetric, in fact, these 2 things are solutions. So this is related to what I mentioned before on the non-uniqueness of the brachyflow. These are brachyflows. And here you also have non-uniqueness. You can have in certain situations like these, more than 1 flow out. You can be separating one way or the other way, and this can happen. I mean, this at least in the very regular, very symmetric case does happen. It's an open question, when does it happen in general? I mean, when you have multiple solutions and when you don't. This is not known. And in the picture that I had here, and let me go back to the picture that we were discussing before, you're going to have, of course, more nodes. You can count exactly how many nodes that you're going to have, and you're going to find solutions. The existence of these solutions, it's a paper by Rafe Mazzeo and myself. In the case of 3 curves, it was a previous paper by Oliver Schnurrer and Felix Schulze. And in that case, you do have uniqueness. But in our case, we basically look at networks that are minimizing networks in this particular metric that I was talking about that I didn't completely describe, but we're looking at minimizing networks, and we prove that you can always find one minimizing one, and that in some situations you will have more than one. There's no full classification of solutions that you can have. And in fact, when you have more than 6 curves, as I described before, you can be developing topology. I mean, you could be having things that have an interior that is growing with the network. I mean, not only curves appearing, but also loops appearing inside. These, of course, are not minimizers. They're not stable. They're not the ones that we describe in this long theorem that I'm writing here. This is just saying that there is one, and it's warning that in general there could be more than one. And it's an open problem to try to classify them. Okay, so now I can go back to my this is the example that I was trying to describe, to my main theorem, and try to put the pieces together. So let me go back to this picture here. Basically, our initial condition in the bottom line is gonna be each of the curves. So we're gonna have many copies of things like this. In the bottom line, you're gonna be describing one of the initial curves. This is the time axis, so this is how the node is going to evolve. And in this extra boundary, what you're going to see, it's a self-similar solution that comes out from straight lines that are the tangents to my initial network. And you know that you have one. You have to pick one before starting the procedure that I'm going to describe now to construct the solution. So somehow the procedure starts by choosing a self-similar solution, and you have more than one choice. So in our theorem, you also don't have uniqueness if you don't have uniqueness for self-similar solutions. You have exactly the same non-uniqueness problem. And let me go back to the theorem. Maybe I already here. And this is what the last sentence here is referred to, that the flowouts are classified by the self-similar solution that you pick. You have to pick one. You can always pick one because you know that there is one that exists, but that is going to determine how the rest of your solution is going to look like. And the solutions are going to be different. Okay, so let me try to give you the idea. So let me see how much time I have. Okay, so the first thing that I'm mentioning here is something that I've been avoiding to mention all the time, but it's something that is very well known to people working on extrinsic geometry. That is the fact that reparametrizing gives you additional terms that can be considered as tangential terms in the velocity in general. So in the case of regular curves, the usual thing that you do is that you choose a parametrization that you have 0 tangential velocity. And this is convenient for many reasons. And in some sense, you need to choose something because otherwise, of course, you're not going to have uniqueness because somehow you're going to see the possibility of reparametrizing all the time. In the case of networks, this is different. You need to allow a tangential velocity because otherwise the node would not be able to move, and you want the node to be able to move. If you're trying to minimize, you want it to find the correct position as well. And you need to add a tangential velocity. What is the correct tangential velocity? Of course, in some sense, it's an open discussion, but by now, most people think that, or most people working on networks think this is a suitable description of the network. So you're choosing the tangential velocity that is given by this equation. The normal part of this is the curvature, and the tangential part is something that depends on the second derivative. And this respects what the velocity should be at the node. That is something that you can determine actually in terms of the curvature. I'm not going to do the exercise, but you can do the exercise, and the 120-degree condition tells you that the tangential velocity has a relation with the curvature at that point. It's not 0, but it's something that you can compute in terms of the curvature. And this choice of parametrization, this choice of equation, is related to that, to the fact that you want to allow the tangential velocity at the node to be the correct speed. Now you blow up coordinates, as I said before, And here's a picture of what I was trying to describe before. In the lines that you see below, these are the original curves. They should be curves, actually, not lines. In this hemisphere that you added, you're going to see the self-similar network. And this is sort of going to be your initial condition in some sense. And now you're going to try to describe the behavior of the nodes as well in the other boundary component. That's the one that you have as time evolves. Then the method of proof that we propose is basically try to construct an approximate solution by using these tau and s coordinates that I described before. That's going to look like a power series. For this to work, you need quite regular initial conditions, but later on you can go to a more general case by approximating by smooth initial data. So for now, just assume that everything is super smooth, and then it makes sense to talk about power series. And what you do with this power series that I wrote here, this formal solution, you put it into the equation, and you get a sequence of ODEs that are going to be satisfied by these eta j's. And the first one that you get, that j that I'm writing there in the equation below, should be a 0. The first equation, the first term that you get is exactly the special flow for the self-similar solution. It's exactly what you see when you write the special flow for the self-similar solution. So you see there that just to start this process, you need to pick a self-similar solution. Once you pick that, and you look at the equations that are satisfied the others, it's going to be something that looks a little bit, looks exactly really in this form, but this fj, by that I mean that I'm not being very precise, you get something that depends on the previous terms. And that iteration, as you see, if you want to compute what eta 1 should be, you will need eta 0. So, and to compute eta 2, you will need eta 0 and eta 1. So in that sense, it depends on the self-similar solution that you needed before, that you picked before. This can be solved, not of course completely explicitly, but you can show that there is a solution. You can study the behavior of these solutions. And there's still going to be a degree of freedom when you compute that is given by the initial condition. And by this, we're assuming that the initial condition also has a power series expansion. So we're assuming that it's quite regular. You, of course, need this close to the node. You don't need it everywhere. But just for simplicity, assume that you have a power series expansion. And then proceed in general by approximation of things that do have a power series expansion. Then after that, you will have something that looks like a solution close to the initial time, close to this new boundary, and close to the behavior of the nodes. And the rest is going to be done by an iteration process. By that, for that, you need to study the linearized operator around this approximate solution that you constructed, or that was constructed before. And well, here I wanted to write a little bit, so I don't know if I think I'm gonna stop here and try to answer the questions. Here I was gonna try to write what the iteration procedure was and the estimates that you need to iterate. So I'm just gonna stop here. Thank you very much for your attention. I'm sorry about the technical difficulties.
All right, thank you. Okay, have you got any questions for Mariel?
May I ask something?
Yes.
Go ahead.
Your graph or whatever it is, it has a boundary, right? Where you are sort of basing the vertices, right?
Yes.
This domain is flat in your case, right?
My case is flat, yeah, but you can think about it on a two-dimensional manifold. Something I didn't say, but it's important, is you need to be codimensional 1.
Okay, but if you do it, for instance, okay, my question is there any difference if you do it in a circle, in an hemisphere with positive curvature, or in the Poincaré disk with negative curvature?
There are differences, but you can treat them in the same way. Because locally, for the self-similar part, it's just a there you don't care about it.
Máscara.
Tá.
Paulo?
Fique todo o tempo com máscara, porque ela atende o público.
Tá bom.
E deita do...
Yeah. The advice was good, but just not now.
Yeah, exactly. But yeah, you can treat the case on a general surface. I mean, but you need to be codimension one. The method would work on what you're gonna see. Of course, is different. The behavior is gonna be different, but you can talk about the problem and you can do short-time existence in the same way on any surface.
And the stability of the solution will be the same, independent of the curvature of the where you're embedding these graphs.
No, I mean, in general, actually, our solutions do not need to be stable because you could be, for instance, choosing a self-similar solution that is not stable in principle. So.
Okay, thank you. Yeah, okay, but that was my question, was because I mean, maybe there is some second variation, and right? Okay.
Yes, of course, yeah. But I mean, for the short-term existence, we're not going to be using the stability, although, and this is one of the features of our proof that is, I mean, in the proof that I mentioned before of Felix Schulze, Neves, and Ilmanen, they do need the stability. Actually, they do use the stability. They can only choose stable self-similar solutions.
Okay, any more questions? If not, I have a question. So you did. Can you go back to the blow up picture where you have the spherical blow up? I think it was.
Yes. Let me try to.
Yeah, that one. Yeah, that's perfect. So is this really a sphere or is this a projective space? Because it really looks like a blow up, right? When you use the term blow up,
yes,
it really looks like a real algebraic blow up.
It is more like a projective space. It is more like a projective space. So
just so that I understand, is it so when you blow up by a real projective space, then you have the exceptional line. So you would be treating as each of these curves, which now don't intersect, but they all have a fixed boundary on the exceptional line. Is it? Yes, that's right. That's right. Is this what's going on here? Yes, this is what. But then, I mean, to find the real solution, you have to allow perturbations there as well. But yes, this is more or less what is happening here. So then I wonder if what would happen if you compare this evolution with the curve. You're minimizing for curves in that picture, and then assuming that the blow up is very small. What would happen if you just switched on mean curvature flow for the actual two-dimensional surface, which is the blow-up surface? Yeah, that's a good question, and I don't know what the answer would be. I mean, in some sense, is the curve minimizing flow the particular case of what's happening to curves under the surface mean curvature flow? If you run, right? Do you know what I mean? If you're running the mean curvature flow on the ambient two-dimensional space. Yeah, no, I know exactly what you mean, and I don't know what the answer is, but it's a very good question. Maybe Jorge has thought about this, if he's still online. I don't know. I would be curious. I would be curious if this is really blowing up in the sort of real algebraic sense. Yeah. Right? Because it's a way of desingularizing things like nodes. They no longer intersecting nodes when you blow up. Exactly. I mean, that's exactly the point here. Yes. Yeah. Cool. Yeah. But yeah, so I would be very interested to know if this coincides with the dynamics you would get if you ran the mean curvature flow on the blown up two-dimensional space. Yeah. But yeah. I mean, it's kind of question that is interesting if the answer is yes, and it's interesting if the answer is no, right? Then what is it? Why are they different? I would be very curious. Yeah, no, it's a very good question, and I haven't thought about it, but yes, it would be very interesting to look at. Maybe you can announce the answer next year in the seminar. Yeah, maybe, hopefully. All right. That would be very interesting. Okay, any more questions or comments?
Excuse me, I do have a question. Eduardo here.
Hello.
You said that, well, it's been proved that if you have a convex curve in the plane, then if you modify the flow to be of a constant area, then the curve evolves to a round circle. Yes. I wonder if this, if we can say something about the isoperimetric problem in surfaces. If you take a network and you converge it so that the areas enclosed remain fixed, do we have a general long existence result for this type of flow so that maybe it converges to an isoperimetric solution?
This is a question that I've been working on actually, and the answer is we don't really know. I mean, it's more tricky than one would think it is in the case of networks.
I see.
My guess would be flat no. It's just no.
No, I
Right?
think I think the answer is no, but we cannot prove it. I mean, there are some gaps, let's say, in the proof.
Okay.
Because if you fix the area of every interior region, then someone has to give in.
Yeah. No, I mean, it is tricky. It's tricky somehow to, or maybe it's the approach that we're using. I don't know, but basically, we run into the problem is, are we using the isoperimetric inequality to prove the isoperimetric inequality itself somehow? Because some of the bounds that we need somehow are the type of the isoperimetric inequality. But
Okay.
I don't know. The answer is that it's not a simple problem. We thought it would be easier, but no, I don't know.
I have another question which regards, Jorge has a comment here. Sorry, please go on. He's saying that the blow up here is to provide some sort of differentiable structure to the singularities in strata of manifolds with edges of corners. Yes, this is absolutely right. But there's a prescribed way of doing this, which comes from algebraic geometry. There's a construction which is called the blow up, right? And what it does is exactly what you say it should. So it's a canonical way. It looks a lot like what you're doing, but it doesn't look quite exactly. So I would wonder if one chose that procedure of blow up, if this would differ or find the same kind of process that you guys have found. That was my point, George, if that makes sense at all.
Yeah, no, but yeah, I mean, this I think is, I mean, it's certainly inspired on that blow up, but I don't know if it's exactly the same. I guess that's my answer, right?
Okay, yeah. And so my other question would, I mean, you're looking a lot at a sort of local picture near singularity, right, to do the flow outs and so on. But what if you look at the global picture? I mean, if you have a picture with several curves and several nodes.
No, I mean, you can do gluing in general. I mean, if you don't have anything, if somehow you know that you don't have things colliding, if you have enough space between the nodes, the gluing procedure would work here as well. It's just like not so nice to write out, but you can do that. I mean, certainly it's good for gluing, and what would be it's a local thing.
And by flowing out, can you sort of automatically triangulate? Right, because if all the singularities flow out, then you sort of got a triangulation, isn't it?
Right. Yeah. Maybe. Yeah. I don't know.
Potentially quite powerful,
Yeah.
even short time existence.
Yeah. Yeah, but it's a good question. I don't know. It's certainly.
Right. It would be very interesting. Yeah, because then with just short time existence around every singularity, if you could do it, maybe a finite number of times, you could end up just triangulating, and then. So yeah.
It looks to me like yes. The answer would be yes, but I haven't thought about it. I think
cool. Right. So, go
may I
Daniel.
make a last remark? I mean, have you read the papers of Jean Taylor? She was a student of Amgreen, and she did this thing sort of currents modulo 3, right? That is just basically these things intersecting at the same angles that you're mentioning. Did you get something out of her, or that's not the point?
No, I mean, like, she's looking at something that's much more complicated, right? Because she's interested in the bubble problem that you have two dimensions somehow. And of course, that's kind of like a next step here. But it is quite more challenging, I would say. I mean, we don't really understand even well the simple case of curves, trying to look at the thing that she does where you have more possible configurations because you have basically surfaces. we hope that this works for that, but I would think it's more complicated, even to have the correct setup.
Okay, let me know when you get into that. I mean, I would like to learn that. I don't know, right? So that's an interesting topic as well.
Okay. All right. Yeah, any more questions? Sorry, yeah? Did anyone raise their hand? Well, if not, then let's thank Mariel again.